Okay, so welcome everyone once again. And this week we have Srinivas Arigapudi to talk to us about miscoordination under sample-based learning. So over to you, Srinivas.
Thanks a lot, Jonathan, for the invitation to present in the LEG seminar. And thanks a lot, everyone, for coming to my talk. So I'll be talking about miscoordination under sample-based learning. This is joint work with Yuval Heller from Bar-Ilan University. So Yuval is in the audience. If you have any questions, I can direct those questions to him. Uh, I guess. Uh, so before I start uh, with the paper, I'll very briefly talk about game theory and evolutionary game theory. I'm pretty sure that most of you are already experts here, but I think it doesn't hurt to start with the basics. Game theory, as we all know, is the study of strategic situations, and coordination game is perhaps one of a very simple kind of game, especially a two-action coordination game. So in this particular game, and the class of games which we are going to study in this paper are going to be embarrassingly simple, but hopefully you would appreciate the classification which we come up with. Okay, so consider the simple two-action coordination game. We have two players. Each player has two possible actions, A or B. If both the players choose A, then they both get a payoff of 2. If both the players choose B, they both get a payoff of 1. And if they choose differently, meaning one player chooses A and the other player chooses B, then the payoffs are 0 for each player. Given a game, the natural question to ask is what is going to happen? Any game has certain set of players, and then players will have actions. Actions will lead to outcomes. Outcomes will be associated with payoffs. Now, given this game, a natural question is what is going to happen? Classical game theory, the standard solution concept is Nash equilibrium, which is a situation where each player is best responding given what everyone else is doing. And Nash in 1950 showed that there's always going to be an equilibrium in wide classes of games, possibly in mixed strategies. In the simple coordination game which I had shown, what are the predictions? It's clear. There are two pure strategy Nash equilibria. One is where both players choose A, and the other is where both players choose B. There's also a mixed strategy Nash equilibrium in which both players play A with probability 1/3, and with the remaining probability play B. Now coming to evolutionary game theory. So as you've seen, game theory is mostly the standard solution concept in game theory is a static one. In evolutionary game theory, on the other hand, the focus is on dynamics. Here we have, instead of players, we usually have populations. Uh, in general, each population will correspond to one player. And then if we have some symmetry involved in the game, it will be without loss of generality to just focus on one of the population. Just pick one population and then just do analysis. In evolutionary game theory, what we do is we assume that there are agents in a population who are making choices based on simple choice rules. In particular, we do not assume that they are hyper rational. We just assume that they are, in some cases, we assume that they are choosing actions based on imitation. So these simple choice rules can be based on imitation, and sometimes it can be based on optimization and uh, anything in between. There is by now a lot of literature in evolutionary game theory. These are kind of standard references in the field. And very recently, Jonathan has written a very nice reference on evolutionary game theory. So what we have here is evolutionary dynamics, which tell you how the distribution of strategies or actions in the population changes over time. Just to compare and contrast game theory with evolutionary game theory, we have where we have players in classical game theory, we'll have populations. And if the underlying strategic situation is symmetric, game, then we can, without loss of generality, just focus on a single population, which is what we will do later on. Where we have mixed strategies in classical game theory, that will correspond to population shares. So these population shares are the ones which are going to be evolving with time. The solution concept in classical game theory is Nash equilibrium. The solution concept in evolutionary game theory, like strictly speaking, here it should be the limit points of the underlying dynamics. But for the classes of games which we are going to consider, we can just focus on the stable response. Okay. So the two main important questions in evolutionary game theory is, given a game and given an evolutionary dynamic, do the population shares converge? That is question one. It is not necessary that even in games where there is only a unique Nash equilibrium, there can be games where there is a unique Nash equilibrium, but the evolutionary dynamics need not converge to a unique Nash equilibrium. So convergence is not always guaranteed. That's question one. Question two, if at all there is convergence, is the convergence to a Nash equilibrium of the underlying game? So broadly, these are among many questions, these are the two questions which are of considerable interest. And these are the two main questions which we would be also looking at in this particular paper. So before I get into more complicated evolutionary dynamics, let me talk about a very simple, a very basic evolutionary dynamic, which is based on choosing myopic best responses. Again, consider the simple two-strategy coordination game. Figure 1 represents, it shows the best response dynamics in the coordination game. So here what is happening is that there is a single population. The points here on the line will represent a population state. So for example, if I consider a point like this, if I consider point A, this particular point, that is the population state where everyone in the population is choosing action A. And similarly, this is the point. Point B is the population state where everyone is choosing action B. And if I consider a point here, the hollow dot, this is the one which corresponds to the mixed strategy Nash equilibrium of the game. This is the state where 1/3 of the population is choosing A and the remaining 2/3 is choosing B. So generically, if I pick some point on the line, if P is some point on the line between 0 and 1, P will represent the fraction of agents choosing action A. If P is the fraction choosing A, 1 minus P would be the fraction choosing action B. That is the population state. And what do the arrows represent? The arrows represent the direction in which the population moves. So here, what's going to happen is that we will assume that some agents die and new agents enter the population. Whenever a new agent enters, under the best response dynamic, the assumption is that the new agent knows the underlying game. In this particular case, the new agent who enters the population knows that the underlying game which is being played is given by this payoff matrix. The new agent also knows the underlying population state. The underlying population state here would be represented by a scalar, P, fraction of agents playing action A. So if the initial population state, let's say, is to the left of the mixed strategy Nash equilibrium, let's say it is somewhere over here. What the agent does is the agent looks at the payoff matrix, looks at the population, the fraction of agents playing action A, and then chooses a myopic best response. In this particular game, if the initial state, as you can see, it's a very simple computation. You can very easily verify that if your initial population state is such that it is to the left of the mixed strategy Nash equilibrium, the new agent will choose A. As a result, eventually what is going to happen is that if the initial population state is to the left of the mixed strategy Nash equilibrium, everyone in the population is eventually going to choose A. That is being represented by these arrows. And similarly, if the initial population state is such that it is to the right of the mixed strategy Nash equilibrium, then eventually everyone is going to choose action B. So what the figure represents is the best response dynamics. And as you can very easily see, under the best response dynamics, only coordination is stable, meaning nothing in the interior is going to be stable. And also, one can show that under many evolutionary dynamics which are commonly studied in the literature, miscoordination, meaning something in the interior, is going to be unstable. Again, I'm not defining many here, but this will certainly include replicator dynamics and many other standard dynamics which are studied in the literature. Okay. What we are going to do in the paper is going to study a variant of the best response dynamic. I'll come to the variant which we are going to study in the next slide. So let me talk about a couple of variants of best response dynamics. The best response dynamics is already something which I had explained. This is where this was introduced way back in the 90s. So here, as I said, the assumption is that the new agent who enters the strategic situation knows the underlying game and the population state. The new agent just plays a myopic best response. This is the best response dynamics. Another possible variant here could be the case where assume that the new agent knows the underlying game. So, for example, in the example which was given, the new agent knows that it is a two-action coordination game which is being played, and also knows the entries of the payoff matrix. But let's say that this new agent does not know the population state. So this new agent does not know the fraction of agents who are playing action A and the fraction of agents who are playing action B. A plausible process here would be that this new agent might observe some 100 people choosing something. So maybe he or she will draw a sample of, let's say, size 100, sees 70 people choosing A and 30 people choosing B. Then what this agent does is assumes that this sample is representative of the true population state, and then chooses a best response to this sample estimate. That is another possible dynamic. What we are going to study in this paper is another variant where if you want to think of this, it would be like a complete 180 degree of the best response dynamics, where in best response dynamics, the new agent knew the underlying game and also the underlying population state. Here, the assumption is that the new agent knows neither. They do not know the underlying game, and also they do not know the population state. So what do they know? The new agent only knows the set of actions available to them. In the example given, the new agent knows that there are two possible actions. So knows that action A is a possibility and action B is a possibility. What the agent does is that tests each action k times, and each time this action is going to be played against a newly drawn opponent from the population. And once the testing phase is done, for each of the action, there is a certain payoff which will be associated. There is this experience which the new agent acquires based on these tests, and then chooses the action which has given them the highest payoff. So this dynamic is in some sense should remind you of some form of reinforcement learning, where you do not have information of the underlying strategic situation or the underlying population state. You are only responding to the experience payoffs. Great. Just a quick summary of the dynamics which I had explained and the associated informational assumptions. Under best response, you know both the underlying game and the population state. Under sampling best response, you only know the underlying game. You do not know the population state. Population state here is the distribution of actions which are being played by the population. Under best experience payoff, you do not know the underlying game or you do not know the population state. All you know is the set of actions available. Uh, Before I move on, let me know if there are any questions, clarificatory questions, Subha. Okay. Okay. So today's talk is going to be about best experience payoff dynamics in two-action symmetric coordination games. This is joint work with Yuval Heller, as I already mentioned. And this is actually a follow-up to what we had done earlier. In an earlier paper, which was published recently in AJ Micro, we studied sampling best response dynamics in coordination games. This is a follow-up work to that. And towards the end of the presentation, I'll try to compare and contrast the results between these two dynamics. Great. So coordination games under best experience payoff dynamics. Before I introduce the model formally, first let me go through the summary of main results, and then I'll introduce the model. So here, as I said, it's embarrassingly simple class of coordination games. Most of you are already aware of these kinds of situations. This would probably be like Econ 101 kind of games. So here we have two action symmetric coordination games. We have two payoff parameters, U and V. We assume that U is greater than V. This ensures that this particular action profile, A comma A, is a Nash equilibrium. And then we choose these payoffs of 0 and 1. These are just normalizing constants. We could have come up with other payoff parameters, but it is without loss of generality to assume that this is 0 and this is 1. As I said, we will be considering best experience payoff dynamics. Great. So result 1 is where we come up with a sufficient condition for which we get coordination to be globally stable. So this is the case where we get back the benchmark result. In particular, what we show is that if we have a K which is at least as big as 2, and if we have U, if U is greater than 0 and V is less than 1, then only coordination can be globally stable. Meaning that if you run best experience payoff dynamics, even if the agents do not know the underlying payoff matrix, if they are using best experience payoff dynamics with a sample with K of at least as big as 2, then eventually everyone in the population is either going to choose A or is going to choose B. That is the benchmark result, which is true for many evolutionary dynamics. And we also provide necessary and sufficient conditions for miscoordination to be globally stable. Here, miscoordination I'll formally define it at some point later, but miscoordination is just a population state where it is an interior state. So if you are on the line, you are somewhere in the interior. That is miscoordination. And we provide necessary and sufficient conditions in terms of the payoff parameters, U and V and K. Great. So before I move on, what we really like in the paper is coming up with this classification of very well-known symmetric coordination games. So we were actually, both Yuval and I, we tried to find if they were earlier classifications of symmetric coordination games, which were done based on the conditions which we obtained. In particular, what we have here is if V is greater than 1, then this is a situation where I will always prefer my opponent choosing action A. That is one possibility. And there's also another possibility where U is greater than 0. This is the case where I would always prefer my opponent to choose B. In these two cases, coordination, something in the interior can be stable. Whereas in other cases, which we call as match me, and again, I should probably say that the other shaded area where V is greater than U is not something which we consider because that corresponds to a game which is not a coordination game. So we are only restricting ourselves to the diagonal and below the diagonal. So these are the match me games where u is greater than 0 and v is less than 1. These are the cases where we prefer opponents to match our own actions. So this is the classification. And if someone has seen this kind of classification somewhere, we would be very happy if you could let us know if you'd seen some kind of classification based on this. Okay. And once I write down the dynamic, when I explain how we write down the dynamic, it'll be clear why we get such a classification. Okay, great. So now let me now move on to the formal model. So these are the two action symmetric coordination games. As I said already, 0 and 1 are just normalization constants. And it's very easy to compute that there are two pure equilibria under the restriction that u is greater than v. There are two pure equilibria, one where both players choose A and another where both players choose B. And there is also one interior equilibrium where both players play A with a probability which is 1 by 1 plus u minus. We now have a unit mass of agents in a population. Agents in the population are randomly matched to play the underlying coordination game. The population state, we can either use A or B. In this paper, we use A as a population state. So P of T is going to be the share of agents who play strategy or action A at time T. 0, the population state 0 would correspond to the case where everyone in the population is playing action B. And similarly, 1, population state 1 would correspond to the case where everyone in the population is playing action A. We assume that agents die at some constant rate and are replaced by new agents. The dynamics, the evolutionary dynamics are going to be given by this differential equation. There are two terms. The W term is something which we are going to explicitly compute for the best experience payoff dynamic in a couple of slides. But first, let me try to explain these two terms. There is this inflow term. W of P would tell me the probability that a new entrant, a new agent who enters the population, what is the probability that this new agent chooses A when the underlying population state is P? That is the inflow term. And then there is the outflow term. Since agents die at random, P, this agent who dies, the probability of that agent who's leaving the population, who was playing A, the probability of that would be P, because agents die randomly. This net effect gives me the change in the fraction of agents who are playing action A.
So can I ask a question here?
Yeah, sure.
Yes. So you say that agents die at a constant rate of 1. What is in 1 per what? Per second, per year?
So it would be 1 per second. I think something. It is some constant rate.
Because you have you have continuous time dynamics, right? So what does it mean that? Okay. Anyway, so you see what I mean here.
Okay. So yeah, let me try to maybe explain it slightly differently. So what's happening here is we actually most of these evolutionary dynamics, they will be you can write down a finite population model, and then what one can show is that as the population size increases, you can approximate the underlying stochastic process using this differential equation.
Good, thanks. It makes sense. Thanks.
Okay. So now the goal is to characterize the limit points of these dynamics. Some standard definitions. P star will be said to be a stationary state if it is a rest point of the dynamics. A stationary state will be unstable, is said to be unstable if nearby trajectories move away from it. In our case, coordination will be said to be globally stable if almost every trajectory converges to the set 0, 1. As set 0 is the case where everyone plays B, and 1 is the case where everyone plays A. And miscoordination is said to be globally stable if states 0 and 1 are unstable. Just to give a simple illustration of the stability definitions, again, let's go back to our simple example. In this particular case, as you can see, the mixed strategy Nash equilibrium will be unstable. Why is it unstable? It is unstable because if you start even slightly to the left of this population state of the mixed strategy Nash, you would go to A. And if you start slightly to the right of it, you go to B. So no matter how small the perturbation near the mixed strategy Nash, you would move away from it. That is the reason why it is going to be unstable. And under the best response dynamics, it is clear that this particular state 1 by 3 is unstable. Coordination is globally stable, meaning that eventually everyone is choosing the same action. Either it is A or it is B, depending on the initial population state. Okay. Before we write down the explicit dynamics, the function W, let me once again recall what's happening under the best experience payoff dynamics. Here, a new agent tests each action k times, and each time the action is being tested against the newly drawn opponent. And then the agent chooses the action whose payoff was highest during the testing phase. And we'll also have to be slightly careful. There can be some degenerate cases where there is a tie. Just to explicitly write down the dynamics, we'll have to mention a tie-breaking rule from the onset. We assume we break the ties in favor of A. We could have broken ties in favor of B, or we could have also broken ties uniformly. The final results which we get will all be qualitatively same. But just to illustrate our results, we'll assume this tie-breaking rule. And whenever there is a tie, we assume that it is action A is favored. Okay. So now this is an important slide. Here we will try to write down the W function explicit. Okay. So let P be the fraction of agents playing action A. Now, let's say I'm a new agent. I'm trying action A. I try action A k times, and each time it is going to be against a newly drawn opponent. So when I try action A, I will have a sample of size k. In this particular sample, when I try action A, I call this A sample. This sample will be of size k. In this particular sample, there will be certain number of A's and certain number of B's. Since P is the fraction of agents playing action A, if I consider the number of A's in my A sample, this will be a binomial random variable with parameters K and P. So when I test action A, I get a payoff of U whenever I encounter someone playing action A. I encounter someone playing action A X number of times. So each time when I encounter someone playing action A, I get U. I encounter X such A's. As a result, U times X is the payoff which I get following that. There are X number of A's and K minus X number of B's. Each time I encounter someone playing action B, I get a payoff of 0. And 0 times K minus X is just 0. So the payoff which I get when I test A will be U times X. Let me know if there are any questions here. Okay. Very similarly, I'll also try action B. When I try action B, I'll call it a B sample. My B sample will also be a sample of size K. Again, the number of A's in this particular B sample will again be binomial. The important thing to note is that this Y here will be independent of X. And now when I test action B, whenever I encounter A, I get a payoff of V. I encounter Y such A's, as a result of which I get a payoff of V times Y. And when I have Y number of A's in my B sample, there will be K minus Y number of B's. And each time when I encounter B, I get a payoff of 1. So the payoff of testing B will be this much. And when will the new agent choose A? Given our tie-breaking rule, the new agent will choose A whenever the payoff of testing A is at least as good as payoff while testing B. So if I combine all of this, I choose A to B whenever this condition holds. So if I combine that, the W function which I have will be given by this. So when will I choose A? I choose A whenever this happens. The probability of that is given by this. This is the inflow term. So just to summarize all of that, the K best experience payoff dynamics in the class of coordination games which we have, it will be given by this particular equation. It has this inflow term and then the outflow term, where X and Y are IID binomial random variables. Any questions with respect to the dynamics? Okay, so let's then move on. The one thing to note here is that the first guess which we had once we written down the dynamic is that we thought that if the coefficients of these binomial random variables, u and 1 minus v, our first initial guess was that if these things were positive, then this would be a well-behaved function, in the sense that we thought that we would get back the results from earlier evolutionary dynamics where only coordination would be stable. So that was our guess. So if you recall the classification which I had shown in the very beginning, it crucially relied on u being greater than 0 and v being less than 1. And it comes from these two things. And it was initially just a guess, but thankfully we were actually also able to prove it. So the first formal result we have in the paper is that if we have K, which is at least as big as 2, and if we consider coordination game, U is always greater than V. That is always there. And if we impose this additional restriction that U is greater than 0 and V is less than 1, and where are these two things coming from? As I said, it was just a pure guess based on the form which we had seen. If we impose these two coefficients to be non-negative, then what we show is that there exists at most one interior stationary state. And it's not saying that there will always be an interior stationary state. There can be cases when there is no interior stationary state. In such cases, it's actually pretty obvious that only coordination can be globally stable. Again, I'll show you graphically why that is the case. So what this is saying is that there exists at most one interior stationary state. And if at all such an interior stationary state exists, then it is going to be unstable. That is our first result. Before trying to give a sketch of the proof for the result, let me try to illustrate the result using graphs. Okay.
Can I maybe ask something?
Yeah, sure. Yeah,
I
sure,
don't
please.
really understand how you get an interior steady state if you do the tie breaking. Because if like you are stable inside, like you have an interior stable state, so you should get an equal payoff if you play A or B. And then you would play A and go to A. So it shouldn't be stable.
So let's get back to this particular equation. from which we derive the best experience payoff dynamics. So generically, for any given values of u and v, this is actually never going to hold with an equality. The tie-breaking rule which we have, it is actually not very important. For generic values of u and v, this is actually never going to hold, this particular equation which we have is actually never going to hold with an equality.
But don't you need it to hold to get an interior stable state?
No, we do not.
Okay.
So maybe a better example here would be if we are considering the best response dynamics in this particular game, the W function which we have, it will be 0 until a certain threshold. It can be any value between 0 and 1 at the interior Nash, and beyond that Nash, it will be 1. So generically, we will have an interior stationary state. Under many evolutionary dynamics which we study, there will always most likely be an interior stationary state. But the point is that will be unstable. The picture which could be helpful is to think of plotting best response dynamics in this simple case. Yeah. Okay. So let me try to illustrate the result which we have through these diagrams. Let's fix the payoff parameters to be 2 and let u be 2 and v be 0. And let's say that k in the left panel, k is 2. Here, as you can see, the W function is always above the 45-degree line. So the net effect we consider P dot, which is W of P minus P, is always going to be positive, as a result of which eventually there is going to be convergence to the state where everyone is playing A. And then to the right, we fix the payoff parameters, u to be 2 and v to be 0. We increase the sample size. We increase k to be 6. And even before looking at the specific instance, it is intuitively clear that if I fix the payoff parameters of the game and if I increase k, then I get better and better estimates of the underlying payoff situation. So what must be true is that if I fix the underlying game parameters and take k to be very large, then the behavior which I get under very large k should be qualitatively similar to the behavior which I get under best response dynamics, which is something which you can notice here. As I said, under the best response dynamics, there is going to be an interior state, which is going to be unstable. A very similar thing is also going to happen here. The interior stationary state, the place where it happens, that will be different under various dynamics. But qualitatively, what is going to happen under many evolutionary dynamics is that there will be some interior stationary state, which is going to be unstable. And the reason why it is going to be unstable is also clear from the illustration which we have here. As you can see, the function w, it intersects the 45-degree line from below. So what's going to happen is that if you evaluate the derivative at that particular point, at that stationary state, it will be greater than 1, because of which it will be unstable. Okay. So how do we prove this result? And just recall that these are the dynamics, and the W function which we derived, it will be given by this probability where X and Y are IID binomial copies drawn from with parameters K and P. This is the coordination game condition where U is greater than V. This is the match me condition where U is greater than 0, V is less than 1. The result, the theorem I've written almost. I'll tell you why it is almost and not immediate. The result follows if we can show that W has at most one interior fixed point. So what we show is that the crucial part in the whole proof is to be able to show that this particular function W, this will have at most one interior fixed point. That I think is a very nice math problem. If you are interested, you can try out the proof. We have a proof of it in our paper. We think it's a nice math problem. So I encourage you to have a look at it if you're interested. So that is the main part of the proof. And the almost is there. It is because once we are able to show that there is at most one interior fixed point, what we can very easily show is that if there exists an interior fixed point, we can very easily show under the given restrictions that the W function will intersect the 45-degree line from below. So if an interior stationary state exists, then it will be unstable. So that part is not very hard, but the non-trivial part is to show that this function W has at most one interior fixed point. Any questions, any clarificatory questions before I move on?
I have a question.
Yeah, sure.
Does this interior fixed point correspond to mixed strategy Nash equilibrium of the game?
In general, no. For small values of k, it will be different. But as you increase the sample size, meaning as you increase k, it will get closer and closer to the mixed strategy Nash.
Okay. It makes sense. Thanks.
Yeah. Yeah. But the crucial point is that whenever such an interior stationary state exists, it will be unstable.
I see.
Yeah. Any other questions? Okay. So that is result one. And then we have a few more results, but I'll just complete with the second result. And maybe towards the end, tell you what else we do in the paper. So the second result, we come up with conditions under which miscoordination can be globally stable. Before explaining these conditions, let me tell you how we get these conditions. So what you need to do is you just need to ensure that the boundary response, state 0 and state 1, they are unstable. Once you impose those conditions, you get this. That's the mathematical side. But if you want to just look at this condition, it's kind of intuitively, well, I should not say intuitively clear because it's once you've written down the dynamic, everything is intuitively clear. But at this point, what should be clear is that for something different from known behavior to occur, the sample size cannot be too large. So what I said earlier is that if you fix the game parameters and if you increase the sample size, if you increase k, then the qualitative behavior which we get under BEP dynamics will be similar to best response dynamics or most other evolutionary dynamics. So in order to get behavior which is different, qualitatively different from the existing dynamics, one condition which almost is essential is that the sample size k cannot be too large. That you can see from this condition. If the sample size is not too large, the too large will depend on the underlying game parameters, then miscoordination can be globally stable. So I'll also try to explain how we get to these conditions. Okay. But before that, a simple graphical illustration. As I said, for something in the interior to be globally stable, we impose two restrictions. We want state 0 to be unstable, and we also want state 1 to be unstable. Mathematically, what we want is W prime of 0 has to be greater than 1, W prime of 1 has to be also greater than 1. If we impose those two restrictions, then we get to this. But let me also try to give an intuition of how to get to one of those things. Okay. So let me try to analyze the stability of the population near the state B. So this is, recall that B is the state where everyone is choosing action B. So epsilon is the fraction of agents playing action A. At if you're trying to analyze the stability of a state B, you'd be looking at states near B. If you're near B, then very small fraction of agents play A. So you can assume that there is some small fraction epsilon, which is very small compared to 1. Those fraction of agents play A. If you're doing stability analysis, only terms of order epsilon will matter. So if whenever I'm computing payoffs from my samples, I'll only have to worry about one surprise in my sample. Surprise here would correspond to the rare action. In this particular case, the rare action would correspond to encountering someone playing A. So now, if I encounter a surprise in my A sample, then k minus 1 times I encounter someone playing B, because of which I get a payoff of 0. And once I have a surprise, I encounter someone playing A, because of which I get a payoff of U. So there is only surprise in the A sample. Playing B gives me K. So if U is at least as big as K, then state B will be unstable. That is one case where state B can be unstable. Another case where state B can be unstable is when there is a surprise in my B sample. So if there is only one surprise in my B sample, playing A will always give me just a payoff of 0. I'll just get 0 K times. And playing B gives me 1, K minus 1 times, and V the other time. State B will be unstable when this payoff will be at least as big as this. Combining these two things and also assuming that U and 1 minus V are not integers, we can say that state B will be unstable if and only if the sample size K is not too large. Not too large is here the max of U and 1 minus. That is the case where state 0 is unstable. You can do a very similar analysis and show that if K is not large than this, then state 1 is unstable. Combining these two conditions, you get this result. Okay. So what I had shown is only for the cases where there is homogeneous sampling, where we assume that everyone in the population is testing the same number of times. K is the same. But of course, a more realistic model will allow for heterogeneity in K. We also do that in the paper. Again, in order to keep the notation simple, I did not go through it. Before I conclude, I'll maybe just give a brief comparison with the results which we already have from our earlier paper. So as I said, in our earlier paper, yeah.
Excuse me.
Is there any question? Yeah.
Can I just give a suggestion?
Yeah, sure.
So a very nice result. I think it would be good if you would illustrate the condition you had on K and U and V. You had an inequality there, right?
For result 2?
You had the inequality there. This one, K less than.
Yes.
For the observer or reader, I think it would be nice if you draw a diagram with U and V on the vertical and horizontal axis.
Okay.
And one could then see where is, how big are these things and where are the regions?
Mm-hmm.
Just a graphical illustration of the inequality.
Okay.
Yeah. Thank you.
Okay. Yeah. Thanks a lot for the suggestion. So I think if I understand correctly, you would. So you would want a picture like this would be something which you would suggest, right? Professor Webel, I think you are muted.
Yeah, just to give an idea of which combinations of U and V will allow for which K and some graphical thing.
Okay, great. Thank you. Thanks. Okay. So comparison with our earlier paper. So as I said, in our earlier paper, we study sampling best response dynamics. Just to recall, under sampling best response dynamic, new agent knows the underlying game, but does not know the population state. So the new agent observes k random choices of the opponents and then best replies to their sample. In that paper, what we show is that for miscoordination to be stable, sample sizes have to be heterogeneous. Meaning, if everyone uses the same sample size, then only coordination will be stable. And we come up with other results which show that if there is sufficient heterogeneity in the sample sizes, then miscoordination can be locally stable. That is, there are other things also which we do in the paper, but the thing which is relevant to us here is this particular result. Whereas under the best experience payoff dynamics, what we show, among other things, is that miscoordination can be not just locally stable, but it can actually be globally stable, even when the sample sizes, even when sample sizes are are homogeneous. Great. So just to conclude, what we do is we study coordination games, a very simple class of two strategy coordination games. As we all know, they have two types of equilibria: pure equilibria, where there is coordination, and an interior equilibrium, where there is miscoordination. Existing literature shows that under many evolutionary dynamics, there is global convergence to pure equilibria, where everyone is choosing the same action. Our result shows that there is a plausible dynamic which is based on sampling, which has been studied in the literature, the so-called best experience payoff dynamics. Firstly, we study this dynamic and come up with sufficient conditions under which we get back the benchmark result. That is the first main result. And then we also come up with conditions under which this dynamic can generate qualitatively different behavior. Meaning, in this case, we come up with conditions where miscoordination can be globally stable. So that's all I have for today. And thank you all once again. Be very happy to take questions, comments, or any feedback. Thank you.
Can I ask one more question?
Yeah, sure.
So when you have the instability condition is fulfilled, so what do the solution trajectories look like? How does the population behave? I mean, do we know that how trajectories look? How they behave in state space?
Yeah, so this is one particular illustration. The left panel here is the case where U is 5 and V is 4.5. In this particular case, we actually have globally stable point. This is where all the trajectories converge.
Right.
Okay. Perfect. Thank you very much, Srinivas. We can move to non-clarificatory questions.
Yeah.
I'll stop the recording.